Hello, everyone. I am Mitsunori Uemura of Ritsumikan University. Let's start the second week of the Advanced Topics in Robot Control. First of all, to clarify why you learn robot control, I would like to introduce the significance of robot control in recent years. With the recent innovations of AI-powered robots are expected to change the world's economy. This kind of change has already begun. In fact, shipments of industrial robots have quadrupled in the last decade. Robot control contributes to the accurate, quick and energy-saving operation of such robots. However, today's industrial robots can't perform as skilled a task as humans do, and many tasks are still performed by humans. In order for robots to replace these tasks, industry requires further innovation of robot control. Several new robot industries are emerging, and cleaning robots are starting to work in our homes. In the future, mobile robots are expected to perform a variety of tasks in addition to cleaning. In fact, many venture and major companies are actively researching and developing mobile robots. In order for such mobile robots to efficiently perform tasks on behalf of humans while avoiding falling, many technological innovations are still needed, and the innovations of robot control is also required. Although you don't have an often chance to see it directly, logistics robots are already widely used in practice. Such robots are used in the warehouses of companies that handle huge volumes of products, such as Amazon, to store, organize, and pack products into boxes for shipping. However, there are many tasks that are still performed by humans, such as boxing up a wide variety of products and moving packages into trucks. Further automation is required in the future. For further automation, we need more advanced robot control that can cope with variety of conditions so that a wide variety of products can be packed into boxes. Medicine is one of the important fields where robotics are making a significant contribution. Surgical robots offer a lot of benefits to medicine. For example, in area lacking doctors, surgical robots enables highly skilled veteran doctors to perform operations remotely. In addition, surgical robots can easily scale their motions, enabling delicate surgeries that cannot be performed directly by humans. In addition, the surgical robot can get rid of undesirable oscillations caused by humans' hand tremors. This provides more stable operations compared to normal human surgery. Robotic surgery is also effective in preventing infections from surgeons to patients, because we can remove bacteria and viruses relatively easily from robots. Infections from patients to surgeons can also be prevented, of course. By optimizing the structure, mechanism and shape of the robot, robotic surgery can minimize the damage to the body of the patients. Further improvements are expected in the future. For example, surgery assistance, motion limitation for preventing injury from living tissue, or fully automations. To realize these improvements, more advanced robotic control is required for the field of medicine. Several other robots are also attracting attention. Robots that work in environments where humans cannot enter, such as in space or in nuclear reactors, are also already in practical use. The advancement of robots that support human motions, such as prosthetic limbs, prosthetic legs, walking assist robots, and rehabilitation robots, has also been remarkable. Humanoid robots that can move in a human living space are expected to perform the delivery automation. Medical examination robots that prevent coronavirus infections may be developed soon. World economy predicts explosive improvements in robot functionality with rapid growth of AI and self-driving car technology that enhance environment recognition ability of robots in the near future. Advancement of robot control is essential for such technological innovation, and it is really significant for you to learn robot control. Next, before introducing a concrete robot control, I would like to explain the relationship between robot trajectory planning and control. When we control a robot, the first thing to do is to set the desired task. This means deciding what you want the robot to do. Once the desired task is decided, the next step is to design how to move the robot to carry out the desired task. In other words, design the desired motion of the robot. This process is called planning or motion planning. After the desired motion is planned, the robot is controlled so that the robot actually moves according to the desired motion. This is called robot control. Sometimes the motion planning and control are clearly separated, but sometimes they are not. Control may include part of the motion planning, or the motion planning may include part of control. This class mainly introduces robot control. To specifically understand planning, I would like to introduce some examples. First, let's think about manufacturing. In manufacturing, the robot arm grabs and moves mechanical parts to machine and assemble them. In order to perform such task, the hand of the robot needs to move to several predetermined positions at predetermined times. Planning is to specify such positions and times. The motion planning determines the position of the robot hands to accomplish the desired task. The method of determining the desired hand position that does not move is called point-to-point control, PTP control. In this case, the desired hand position vector xt is a constant vector, and time derivative of xt is then a zero vector. This method does not specify a path from the current position to the desired position. Therefore, PTP control is suitable for tasks such as pick-and-place tasks where only the final position to reach is important. The other method for determining the desired hand position that moves over time is a method called continuous path control, CP control. In this CP control, the desired hand position vector xt depends on a time, and the time derivative of xt is the desired hand velocity. CP control continuously specifies the position where the robot hand should pass through, and CP control is suitable for tasks such as painting in which the path of the robot hand is important. The terms PTP control and CP control are often used in the field of robot control. So let's take advantage of this opportunity to understand them. I would like to start concrete introduction of robot control. Before introducing advanced control, let's review PD control, which is the most basic control, by concretely creating a program. Let's use MATLAB and Simulink to create a simulation program. In order to master all the advanced control that I will introduce in the future classes, you should implement them in MATLAB and Simulink. By actually implementing these control, you can understand them deeper and more clearly. In this exercise, we consider the one-link robot that moves in a plane where gravity does not act as shown in the illustration. You should implement PD control that enable the robot joint angle Q converge to the desired angle QD. To do this, we create a robot simulation using MATLAB and Simulink. As I'll explain in detail at the end of this video, this exercise is homework for this week. To create a simulation, you first need to derive the motion equation of the robot. If you forgot how to derive the motion equation of the robot, please review the mechanics. To do this exercise, let's execute MATLAB program. When you execute MATLAB, a screen like this will appear. After MATLAB is started up, type Simulink in the command window and press Enter to launch Simulink. When Simulink is started up, you will see a screen like this. In Simulink, controlled objects and controllers are placed in the blank area like a block diagram to create a simulation. We call this area simulation model. Click Library Browser in the upper left of the window to place the controlled object and controller. When Simulink is started up, you will see a screen like this. In Simulink, controlled objects and controllers are placed in the blank area like a block diagram to create a simulation. We call this area simulation model. Click Library Browser in the upper left of the window to place the controlled object and controller. When the library browser is started up, a window like this will appear. The library browser has blocks with various functions. When you create a simulation, you paste some blocks into the area of simulation model. Drag MATLAB function in user-defined functions and paste it in the blank area of the simulation model. Then, the block of MATLAB function is placed like this. This block is assumed to represent the controlled object, that is, the physical robot. To edit the program inside this block, let's double-click on the MATLAB function block. Then you can edit the program source using like this screen. The first line of the program source describes what the output and function name and input of this block are. In the case of the robot, the input is joint torque tau and the output is joint angular acceleration ddq. Let's name the function robot dynamics. Therefore, let's change the first line like this. Next, let's calculate the output ddq from the inputs tau. By using the motion equation of the robot, you can derive the relation between the torque tau and the joint angular acceleration ddq. Then, you can write a program that calculates ddq. As in this exercise where we consider the one-joint robot with no gravity effect, the joint angular acceleration ddq can be calculated from the input tau using this equation, where m is the mass of the robot link, lg is the length from the robot joint to the mass center of the link, and I is inertia moment of the link around the mass center. Save the simulation model data after changing the program. Then, looking at the model of Simulink, you can see that the name of the block, the input, and the output are changed as programmed. Since the output of this block is acceleration, the simulation should integrate the output with respect to time to calculate the angular velocity and angle. To do this, drag integrator from the continuous group in the library browser and paste it into your model. Since we need to integrate twice to calculate the joint angle, paste the two integrator blocks. Because the target of time integration is the output of the robot dynamics block, let's right-click and drag the arrow on the right of the block to the arrow on the left of the integrator. Then, the two blocks will be connected like this. As a result, the acceleration output from the robot dynamics block is integrated and becomes the joint velocity. Similarly, by connecting the output of this integrator and the input to the other integrator like this, the final output will be the joint angle. Next, let's create a block of the controller. For the control block, use the MATLAB function block as well as the robot dynamics block. You can make it using the library browser as before, but we can create it faster by copying and pasting the already existing robot dynamics block. After creating another MATLAB function block, double-click on it to edit the program as before. The control block should inputs the angular velocity and angle and outputs the torque. Therefore, let's write the angular velocity dq in the angle q in the input part and tau in the output part like this figure. Let's name the block controller. Since PD control is used for control, the torque value is determined by the formula shown in this figure, where Kp is the position feedback gain, Kv is the velocity feedback gain, and Qd is the desired joint angle. Because this exercise aims at PTP control, the value of Qd is always set to a constant 1 radian. The position feedback gain and velocity feedback gain can have different values. This control block corresponds to a computer in a real robotics system. The robot joint angle and angular velocity are measured using sensors, such as an optical encoder, and the computer captures the measured data in real time. Based on these measured values, the computer determines and commands the torque that should be generated on the robot joint in real time. This determined torque can be generated in the motor attached to the robot joint by using a motor driver that can control the electrical current. This control block represents this series of processing. After writing the program, let's save the data and display the simulation model. Next, let's connect the joint angular velocity, which is the output of the first integrator, to the input dq of the control block. Therefore, right-click in the middle of the line connected from the first integrator to the second integrator, and branch to connect to dq. Let's connect the output of the second integrator, the joint angle, to the input Q of the control block. Let's connect the output tau of the control block to input tau of the robot dynamics block. We have now completed the feedback control simulation. You can see that the simulation model created on Simulink is almost the same as the block diagram. Next, let's place a scope on the model from the sync of the library browser in order to visually confirm the simulation results. To see the time history of the joint angle, let's connect the output of the second integrator to the input of the scope as shown in the figure. Now, let's press the Run button to check the simulation results. If nothing goes wrong, you have finished successfully. If you get some error messages, correct it. After running the simulation, double-click the scope to check the simulation results shown in a graph. The horizontal axis of this graph is time, and the vertical axis is the joint angle. We can see that the robot arm that was at an angle of 0 radian at time 0 converged to 1 radian, which is the desired joint angle, within about 3 seconds. This concludes the explanation of how to create a simulation program using MATLAB and Simulink. Now, let's return to the explanation of robot control. In my part of this class, the main content is to introduce the 5 basic robot control described here and let everyone understand them. The 5 control are passivity-based control, calculation torque method, adaptive control, learning control, and optimal control. Many researchers in the world have proposed huge kinds of control. However, most of these control are based on these 5 basic control. Therefore, To understand these basic control is essential for understanding advanced robot control. Therefore, in this class, I would like to explain the details of these basic control and introduce outlines of some advanced robot control. Before we go into the details of each control, I would like to introduce the features of each control. First, the features of passivity-based control are as follows. Passivity-based control mainly consists of feedback. Therefore, this control is mainly used for PTP control. Since this control does not use feed-forward, this is not suitable for CP control. This control works even if the detail parameters of robots are unknown. Therefore, this control has a great advantage that it works stably even in uncertain environments. It also has the advantage of low computational cost. Due to these advantages, this control can be easily implemented in actual robots. The characteristics of the computed torque method are as follows. The computed torque method is a method of calculating the feed-forward torque required to generate the desired motion. Feedback is also utilized together with the feed-forward for stabilization. Due to the feed-forward effect, the computed torque method has the advantage that it realizes CP control. However, detailed models and parameters of the robots are required for calculating the required torque. Therefore, the computed torque method has the disadvantage that it is not suitable for systems involving uncertainty. Another disadvantage is that it requires a lot of numerical calculations to calculate the required torque. As a result, the computational torque method needs a lot of computational resources, which sometimes prevent implementation in actual systems. Adaptive control estimates the parameters of robots in real time and calculate the required torque with the estimated parameters. After the estimated parameters converge so that the required torque can be calculated accurately, the robot will be able to follow the desired trajectory and CP control will be realized. Therefore, the advantage of adaptive control is that we don't need to know the parameters of the robots in advance. However, since the computational cost is the same as the computational torque method, it has the disadvantage that it requires a lot of computational resources and is difficult to be implemented in some situations. Iterative learning control is a control method that learns feed-forward torque through control trials. If feed-forward torque is accurately obtained by the learning, this control realizes CP control. This control method also has the advantage that we don't need to know the parameters of the robots in advance, because the feed-forward torque can be obtained by learning. Because the learning is done by very simple calculations, Learning control also has the advantage of low computational cost and easy implementation. However, it has the disadvantage of requiring a controlled trial to learn the feed-forward torque. Optimal control is a method to calculate the feed-forward torque or motion that minimizes the cost function defined by the control designer. Optimal control is then an excellent method that can achieve various objectives such as minimizing energy consumption and controlling in the minimum time. However, optimal control has the disadvantage that the robot parameters must be known. In addition, optimal control requires enormous computations to obtain the optimal feed-forward torque or motion. Therefore, optimal control is difficult to be executed in real time. This concludes the explanation of the main features of basic robot control. If you understand these features, you will be able to choose the appropriate control when you design control for your robot. Now, let's move on to a detailed explanation of each control. First, I would like to explain the details of passivity-based control. The passivity-based control method was established by Professor Emoto from 1981. This control method is a unique technology that was born and has grown in Japan. Ritsumeikan University has made many contributions to passivity-based control. Professor Kawamura, Professor Jan, Professor Ozawa, and I have contributed to this technology. This control method achieves the control objective by adding artificial potential energy to the robot. For example, let's consider the case where a spring and a damper are attached to the joints of the robot as shown in this illustration. The torque generated in the robot joint by this spring and damper can be written as tau equal k beginning parenthesis QE minus Q ending parenthesis minus dQ dot, where K is a diagonal matrix that represents joint stiffness, QE is a vector that represents the equilibrium joint angle of the spring, Q is a vector that represents the joint angle of the robot, and D is a matrix that represents the viscosity of the damper. Ignoring gravity, the total mechanical energy of the robot is the sum of the robot's kinetic energy and the potential energy stored in the spring. Let's imagine how this robot would move if it started to move from some postures. You can imagine that the total mechanical energy is gradually dissipated by the damper and eventually the robot stops at the equilibrium point of the spring. This can be mathematically proved as I will show in later analysis. In other words, by using mechanical energy, the convergence of motion can be guaranteed mathematically even though the motion equation of the robot is nonlinear. Passivity-based control takes advantage of this property. In the passivity-based control method, actuators attached to each joint of the robot artificially generate the torque of the spring and damper. Therefore, the actuator torque tau is designed by this formula, where Kp is the joint angle feedback gain matrix, Qd is the desired joint angle vector, and Kv is the joint velocity feedback gain matrix. The structure of this formula is the same as that of the torque exerted by the spring and the damper. Therefore, we can prove that this control method guarantees convergence of the joint angle Q from any initial angle to the desired angle Qd by using the energy analysis. Since the formula of the controller is the same as that of the classical PD controller, we call it passivity-based PD control here. Now, let's create a simulation on MATLAB that implements passivity-based PD control on a two-joint robot, in order to obtain a deeper understanding of passivity-based PD control and to become familiar with it. To simulate a two-joint robot in MATLAB, edit the robot dynamics block as follows. First, the joint angular acceleration vector ddq should be calculated from the motion equation of the robot. For this calculation, the inertia matrix M and the centrifugal Coriolis term H should be calculated. To define a matrix or vector in MATLAB, write them like this. Let's calculate the details of each matrix and vector elements by yourself. If you forgot the motion equation of the robot, let's review the mechanics. By multiplying the inverse matrix of the inertial matrix to both sides of the motion equation and leaving only joint angular acceleration on the left side, the right side becomes the inverse matrix of the inertia matrix times the joint torque vector minus the centrifugal Coriolis term. In MATLAB, the inverse matrix is calculated by the function called INV. Therefore, the joint angular acceleration vector ddq can be obtained by this code. Next, we should change the input and output of the MATLAB function to vectors with two elements. Click Edit Data button on this screen. Click Tau from the left column and change the size to 2. Similarly, change the size of ddq to 2. This completes editing the robot dynamics block. Let's modify the controller block as well. I don't explain how to modify the controller block here. Therefore, let's modify it by yourself and run the simulation after the modification. Finally, I would like to introduce homework for this week. This week's homework is to create the MATLAB simulation I described this week and submit it as a report. In the report, please include the figure of the simulation model of Simulink, the program source of the robot dynamics block, the program source of the controller block, the simulation result graph, and the explanation of the simulation contents and the simulation result. Please submit the created report through Manabar. That concludes this week's class. Thank you for your hard work.